Good evening and welcome everybody. This is Obi-Wan Pez for N Simplex Pachinko. We are doing our math stream tonight. We're going to start out where we left off last time, which was in the Edwin Moyse book. And we were starting to build out our algebra, very similar to how one builds out the course or abstract algebra rules of the game and comes up with like what is mathematics just as a whole. So the first group of things that we were talking about, we were saying like, okay, if a times 0, let's prove that a times 0 is equal to 0 for all real numbers, a. Then we can start with this equation, a equals a. That's the reflexive property. So it's by the definition of equality that we can then say that. We can then say that a times 1 is equal to a by multiplicative identity. And then a times parentheses 1 plus 0, we turn 1 into 1 plus 0 by the additive identity. And then we can use the distributive property to multiply left distributive property to multiply a times 1 plus a times 0, which ends up leaving us with a plus a times 0 is equal to a. And then in the next line we add the inverse of a to the left-hand side of both equations. So negative a plus a times 0 is equal to negative a plus a. So that's our sums of equals property. And then here we have negative a plus a is 0 and negative a plus a is 0. So we end up with 0 plus a times 0 is equal to 0. Since a times 0 is a member of the real numbers, it is true that 0 plus that member of the real numbers will be equal to that thing. So a times 0. And that's equal to 0, and so proved. All right. Gotta mark my page. We are getting into all sorts of trouble up at school here. Got to get our courses put up in our learning management system by tomorrow night. That's fine. All right, for theorem 2, we have if a times b is 0, then a equals 0 or b equals 0. We're going to do this in a much more rigorous manner. We're going to talk about this in terms of all of our previous items that we had done. And as I had talked about last time, I'd actually, after stream, I popped over to the natural number game by the Xena project, and unfortunately my save on there had disappeared. It was, some old cookie that probably expired. So I went through and knocked out the tutorial, introductory stuff, addition world, and most of multiplication world by using basically the same properties that we have here. So if anybody is interested, it is a really cool project to try to understand how we would teach a computer to do this sort of stuff. And Lean is the software that's working behind the scenes to make it work. Okay. So if a times b is equal to 0, then one of those things must be 0. All right. Now, this is one that I do in pre-calc all the time. We've done it on this channel multiple times, I'm sure. So here we are assuming that the product of A and B is equal to 0. How are we actually going to go through this? And yep. How are we going to go through this and show that we can do the... I'm just losing my mind today, it's fine. How are we going to go through this and show rigorously what we've got? So, the way we do this is that we look at this here. We know that A times B as a property has to be equal to 0. So just thinking about it, we know that at least the other key word that we could use here noise, baby. Thank you for following. I am Obi-Wan Pez. This is N-Simplex Pachinko. We are here for mathy stuff tonight. So welcome on in. Alright, so another way to say this here is at least one of the set AB is 0. Alright, that's not going to help. Yes, good evening. Welcome. If you have any questions about math, feel free to drop it in chat and I will get to it. Since we're just kind of working out of a book at the moment, that's what the pink backgrounds are going to be. We're working directly out of a book. Then I am perfectly happy to be interrupted at any time that you have a question, so feel free. It may take me a minute to just finish my thought or whatever, but you know. Alright, so if we know that at least one of these things is equal to 0, then there are two possibilities. Either both of them are 0, and, well, that makes it nice and easy, because if both of them are 0, then we know that the product of... yup. We know that the product of two zeros is going to get us a 0. Okay, so this leaves us with two cases. Actually, 3, technically. Okay, so either 1, A equals B equals 0, in which case 0 times 0 is equal to 0, and here we know again 0 times 0 is just 0 by our multiplicative there was a multiplicative property, hang on. Nope, I am a full-time math professor at a 2-year college in the mid-Atlantic region of the United States. But I have taught basically every course. There was an actual thing for that. Oh, no. Psst. It was the one we just did. Right. So if we're going like super rigorous, this is how you'd do this. You'd say, okay, 0 times 0 equals 0 is what we got when we just plug in A and B equaling 0. So when we do that, 0 times 0 is going to be 0 by our previous thing here. So since 0 belongs to the real numbers, use theorem 1. Which course is my favorite to teach? That's a tricky question. If only because right now I have basically built out our pre-calculus course with help of a couple of other people. And so like that's my course. I am currently the person at my college who has taught pre-calculus the most, at least at our college. So that's kind of like, you know, pre-calculus. The full pre-calculus sequence at my college is like mine. So it's sort of my baby. But at the same time, I really like teaching Calc 1 and differential equations to the upper, upper math engineering STEM track students, mostly because they just ask like much better questions, much higher level questions. Like they know the basics. And so like if they don't get the algebra, it's kind of like, okay, well, either I'll figure it out on my own, or I can just ask a quick question that's going to get me from point A to point B. Like I know what's missing in my head. um, Differential equations is a lot of fun, and I will jump over every so often here, and just like start doing some diff EQ because it's just fun. So real 200 ping, good evening, welcome. Yep, go ahead and type your question in chat, and I will get to it as soon as I can. Um, if Noise has another question, we can get to that. So again, here we have the reflexive property zero equals itself. And so because it's the reflexive property, this has to be true. So if A equals B equals 0, then A times B equals 0 implies that one or the other is equal to 0. Now here's the other thing, right? A lot of people think that this means or, that it has to be this or that, and it can't be the case where it has both. Now, we know better, just by looking at it, that, yeah, it's perfectly fine if both of them are 0. I am not particularly familiar with the UK educational system, but if you have any particular questions, I can do some research or whatever. Or if you want to explain something to me, that's fine too, because I'm always willing to learn. All right, so our second case is, okay, now let's take that offer, which was that A is, well, actually, you know what? Okay, A is not equal to 0. So this is our assumption. What would happen if one of these things, and I'm choosing A for this case, so 3 all we're going to do is we're going to do the same thing as 2. We're just going to do B instead. So B is not going to be equal to 0. But other than that, it's going to be exactly the same instead of A. Okay, so when A is not equal to 0, this implies that we have A times B equals 0. We can't make any assumptions. You've got to go like from basic principles. So here, if A times B is equal to 0 and A is not 0, this means that A has a multiplicative inverse, which is called 1 over A, which we can multiply to A times B on the left of both of these things. Okay, and technically this is saying that the whole left side is going to be multiplied by 1 over A. On the right, we have that 1 over A times 0. 1 over A is a member of the real numbers, so therefore the stuff on the right is going to be 0. So this is again going to be theorem 1. And then the left side, what we're going to do is we're going to say, all right, look, this being in that order isn't really convenient for us. So I would rather group 1 over a with a, because those two things can do something. So we're going to associate 1 over a times a and leave times b on the outside there. So this should be multiplicative associativity. Associativity by multiplication, right? For R1 times parentheses R2 times R3, it's going to be the same as R1 times R2 parentheses times R3. So here, 1 over a times a is going to be equal to 1 times b is equal to 0 by, again, this is multiplicative inverse. This one. Multiplicative inverse. There has to be one number, and exactly one number, such that that particular multiplicative inverse multiplied by our particular number is going to be equal to the identity for multiplication. We discussed a little bit earlier, last stream, that the multiplicative identity is 1, and the multiplicative identity always looks like 1 over whatever number we picked. So 1 over r times r is going to be equal to 1, and r times 1 over r is going to be equal to 1. So then here, this is multiplicative inverse. And then we're going to take this, shift it down a bit. And 1 times b is just b. Yeah, that's good enough. All right, and this is going to be our multiplicative identity. Whew. Block of text. All right. All right, and theorem 2 ends with number 3, which is going to be the same as number 2, but you're assuming first that b is not equal to 0, and then therefore it proves that a must be equal to 0. So if a is not 0, b must be, and if b is not 0, a must be. So those are our 3 cases for theorem 2. This is what's known as the zero product property. I feel like my hand muscles have degenerated so bad. Haven't been writing on a whiteboard all summer. Alright, too harsh. Blue. Whoa. They changed it. Oh man, that's so messed up. Anyway, I much prefer graph paper. Anyway. So, real 200 ping, let's see. Downloaded a roulette game, probability 0 to 36, and color red and black. Number have the same probability to get chosen. Same to red and black, yep. So you win, you have to choose the right number, yep. There is many combination, like you can combine 2, 3, 6. You have to see the table. Yeah. So let's see. You know what? Let me. Just gonna do awful things. Yeah, maybe. Alright, let's go like that. Okay, interesting. So there looks to be a slight difference in how roulette is put down, but kind of depends on what you're looking at here. So 200, let me know if this is correct. So 0 through 36, and there's not a double 0. That apparently is American roulette. Just to turn the screw a little bit more and give the house just a little bit more of an edge. Starting a course in A-level Further Mathematics. Wondering if it is similar difficulty to an AP course in the US. Okay. And that is an example. Many university maths departments encourage students to take further mathematics at A level, as it introduces a wider range of pure and applied content, such as matrices and complex numbers. Okay, so maybe. I'm reading an article here by wyke.ac.uk that says A-level further maths is not more difficult than A-level maths. It just covers different areas. So anything that won't fit into A-levels, and if you're already doing pretty well at like whatever A-level is or whatever you took previously that would like cover the A-level topics, then they'd be like, all right, go take this because this is more stuff. So I would say that this is probably a parallel to whatever previous math class you probably had. And that, like I said, this is just going to cover different topics. So I don't know about the difficulty or anything like that. I can't speak to it. So use your discretion there. But it appears that other people who are much better versed than I am says that this is just going to be like in the hook. Further Maths describes a course studied in addition to standard level AS and A level courses. In Victoria, Australia, okay, pure modules, formerly known as Pure 4 through 6 or Core 4 through 6, are now known as Further Pure 1 through 3. So slightly different. So noise, it would also probably depend on whether you're doing this as IB, International Baccalaureate, or if you're doing this as just like your particular high school level stuff. What I'm seeing here is that the topics cover linear algebra. Let me... And we'll get back to the roulette wheel just 1 second here. I don't think that there's going to be like a particularly awesome strategy because it is sort of random, especially if it's an online thing, then it should be random. And you're gonna... We can do what's called an expected value just to see what's going to happen. There are many people who probably claim to have some sort of system that works for them, but, you know, who knows? If it is truly random, then there's no way to get it. Alright, so 1 is going to be like linear algebra. That's not what I meant. Alright, matrices, vectors, and linear or geometric transformations. Topic 2 is geometry. Alright, so triangles, circles, and conic sections. You can't see that. Boop, there we go. Topic 3 is on statistics, which is going to cover some of what we were talking about here, and probability. So geometric and negative binomial distributions. Unbiased estimators. Statistical hypothesis testing. And introduction to bivariate distributions. Topic 4 is on sets, relations, and groups. Which is a bit on set theory. Ordered pairs, binary operations. I think we talked a little bit of, or we will talk a little bit about this in the Moyse book. Not very much though. And group homomorphisms, which is not a phrase I have seen since my linear algebra class in senior year of college. So it has been almost not quite 20 years yet. Group 5 here, topic 5 will be on calculus. This is probably what we call calculus 2, looks like. Yeah. Infinite sequences and series. Improper integrals. Working with limits. Yep. And first order ordinary differential equations. And topic 6 is discrete math, which is mathematical induction. Diophantine equations. Fermat's little theorem. Oh man. That's getting into the weeds a little bit there. Route inspection problem. Nice. Now, without me knowing exactly what that is, and recurrence relations. I think that's going to be called the traveling salesman problem. Oh, no, it isn't. Called the Chinese postman problem, or the postman's tour problem. Find the shortest closed path or circuit that visits every edge of an unconnected or undirected graph. So basically you have to hit every road along the way. Yes, improper integrals are the ones where you have to change the limits. So typically you get something that's like, find the limit as b goes to infinity of the integral from 3 to b of I don't even know. X squared plus 1 over x minus 5. I don't know. We'll do that. Nah, that's not gonna work. X cubed minus 5. There you go. So there's that 3. Yeah, that'll work. Yes, so 200. I do math streams every Tuesday night. I just changed that recently. So and that's Tuesday night my time, so that's going to be Wednesday morning your time, and very, very early. But I don't have a Facebook page. I barely have a YouTube page. That's also N Simplex Pachinko. And I don't do a private Discord for, you know, random people. No offense. I do, however, have another Discord that I am in, which does math help. I think it's just /homework. But let me get the actual invite people. Copy. Oh, I'm US East. So. So that Discord channel is not mine, but it is a place to go for homework help. The people who are there are, generally speaking, a bit like me, where they're going to like ask a series of leading questions to try to get somebody to, you know, their particular answer, whatever they need. But we most definitely have taken essentially a pact and been like, yeah, we're not going to answer your question. You are going to answer your question, and here's how you're going to do it. Which for some people is very annoying. It's also generally how I teach in class. So again, for some people, it's really annoying. But my students generally get used to it. DX. Yeah, so I'll see what I can do with this particular problem. I'm not super great at, interestingly enough, right? I mean, I'm not super great at statistics, but yeah, generally speaking, probability I've got pretty decent at occasionally. All right, let's just double check this here. Yeah, it happens. Oh, that's fun. I didn't notice that. The numbers are not entirely... huh. I thought it was all just going to be red, black alternating, but they change them up occasionally. Is it every group of... It's not. Huh. Yeah, no problem. So I do, since you're Canada, I'm US East, so right now it is 9:40, and I generally will stream math from about 9 to 11, sometimes 12, depends how I'm feeling. If we've got energy going in the stream, then we'll keep going. If I've got some, like, emergency gaming to do, yes, yeah, 9:40 at night at east coast of the U.S. So those are just my hours because I only stream once a week for math specifically. I also do gaming on Friday nights, but if you come in and have a math question, I will potentially, be able to answer it while playing a game, or occasionally I will stop the stream and I will open up whiteboard and draw something out. Not all the time, but you know, kind of depends. If it was something like this, right, taking the limit, you can't see that, right? So that's not what I wanted. That one. I knew it was one of them right in the middle. So yeah, if we had something like this, that was, oh, let's do an improper integral, then we'd easily be able to say, okay, let's stop the game for a minute. Let's draw this up and then show you how it's done. So, why not throw this out here anyway, right? Yep. Have a good night. Thanks for stopping in, and we'll see you again. So for this, first strategy is going to be look for any U's that you can get out of here. So if you can find a U substitution, that's going to be your first go-to. So if we let U be equal to x cubed minus 5, then du is going to be equal to 3x squared dx. Okay, and then we're going to say that this is the limit as b approaches infinity of the integral from x equals 3 to b. Blah. Oh, that's disgusting. Alright, x equals 3 going up to b of, here we've got x cubed minus 5 on the bottom, so that's just u. Up top, we don't quite have du. So my recommendation usually is to say, okay, we need a 3 stuck in front of all this stuff, and to balance it out, we need a 1/3 out front. And then down here, we've got the 1/3 there. Here, this is going to make a 3x squared dx. So that's going to be all one thing, so that's just going to be du. Then we have added to that a 3 times 1 dx. So here, this is also going to be a 1/3 as x goes from 3 to b. Of 3 dx over x cubed minus 5. All right, now this is not going to be nice. It's not going to be nice at all. But good news is still doable. So limit b goes to infinity. And let's just do this one, because why not? This is actually easy, right? This is a natural log integral. So now we have a 1/3 natural log of the absolute value of u as x goes from 3 to b. Now, this is also a terrible thing to do, because we have mixed variables. So with a u and an x down here, you don't generally want to do this, but right now I just threw this in because, quite frankly, I don't care. I'm going to bring it back pretty soon. It's fine. Okay, and then plus, we can separate out the limits. B goes to infinity of 1/3. Now what's going to happen is this integral needs to be broken up. It needs to be split into multiple integrals in order to work out what each of the separate pieces are. So the way to do this is to say we want this x cubed minus 5 to be broken into multipliers, so factors. This is not going to break up nicely, but at the same time it's doable. So there's kind of a few ways we can do this. One is to say, let's do something really nasty and make this 3 times x squared plus 3 times bx plus 3 times c all over x cubed minus 5, and say, well, it's just not factorable, and we'll just leave it like that. This can work. Come to think of it, I don't think we can do it any other way. I think we're kind of stuck. That's not what we want to do. It's close, but it's not quite. Anyway. My mistake. No. What we want to do is say that 3 divided by x cubed minus 5 is going to be broken up into factors. But again, at this point, no, because that's just going to come back with the same stupid crap. Okay. Alright. I'll bite. This might end up not actually being possible. So let's see. Oh, yeah. Oh, yeah, that's gross. Got an inverse tangent and several natural logs. So, yeah. That's what I meant. Yeah, okay. So this is saying multiply the integrand out into linear and irreducible quadratic terms. So this makes me think that there is actually a linear answer here, but it's gonna be pretty gross. I'm pretty sure. Alright, so if we do x cubed minus 5. Oh. What? Okay, yeah. There. Alright, this gets us to a number that is approximately 1.71. Just shy of 1.71. Can we expand that number, please? Please, Desmos? The calculus occupied a lot of brain space. Yeah, that'll do it. Yeah, just root 5, right? Duh. See, this is the problem, is occasionally when you start thinking about all sorts of stuff, you forget the easy stuff. I had actually been thinking, oh, I just get root 5, because like you set it equal to 0, you bring it over and take the cube root, and just friggin', yeah, completely forgot about that. It's cool. Alright, so if we go with the cube root, boy. Am I muted? So if we do this as cubic, quadratic, linear, and constant, we can do the, okay. I was going to say, I'm seeing my bars go like that, so it should be working. Alright, so we can do this cube root thing. Where here, if we take the, no, not that one. No, that's fine. Alright, this is going to be the cube root of 5. If we multiply that, that's going to be cube root of 25. Yep. So here we have 3 divided by x cubed minus 5. And this is going to be like a term that we wanted to come over here and say, hey, let's split this thing up, because we're trying to figure out what the integral of 3 divided by x cubed minus 5 is, and it's just not working. So we're going to have to break it up and do the thing you hate. Yeah, somebody had thrown out improper integrals as a partial fractions. There we go. Improper integrals as a possibility. That's a negative. All right, and then cube root of 25 times the cube root of 5 is just going to be 5, so 0. Yep, I agree. So here we can do a over x minus cube root of 5 plus bx plus c over that quadratic. So this is x squared plus cube root of 5x plus cube root of 25. Now, if you just look at this, this is actually very similar. It's not the same. It's very similar, though, to binomial. But, like I said, this one doesn't quite have it. Dx. Alright, so if we've got a over x minus cube root of 5 plus bx plus c over x squared plus cube root of 5 times x plus cube root of 25 is equal to 3 over cube root, or x cubed minus 5. Then these are going to multiply through, same as we did before. Algebra is just really symbol manipulation, so, you know, understanding the stuff that's behind it is really the important part. The symbol manipulation is just something that happens when you know, understand this stuff at a slightly deeper level. If you work at it, it's going to come. It's just going to be slow. Alright, a times that quadratic Okay, so as we go across, there are going to be x squareds, so ax squared here and a bx squared here. This means that a plus b is going to have to be equal to 0 because there are no x squareds on this side. Then here we've got a plus cube root of 5 times ax, And over here we've got now the singles. So this is going to be CB or CX, not CB. CX plus minus a cube root of 5bx. So this is going to say that our linear factors are also going to be 0. So c minus cube root of 5b is equal to 0. And then our constant terms are going to be cube root of 25 times a plus c time minus minus cube root of 5 times c. Right, those are our constants. That all equals 3. And now here, those two values. So cube root of 25 times a minus cube root of 5 times c is equal to 3. US East. So I don't give out more information than just kind of generally mid-Atlantic region. So, you know, New Jersey through Virginia / North Carolina, depending on where you draw the line. It's a nice big space. Actually, come to think of it, where does Amatic draw the line? Because Amatic, Delaware, Maryland, New Jersey, Pennsylvania, West Virginia, and Virginia. So it's a nice big area. MIT? No, that's Boston. Thank goodness I did not go there. Yeah. Like run down sort of stuff. I'm from originally small town New Hampshire, so everybody screams that song. Can't get away from it. I'm glad you think so. I found it, you know, somewhat limiting, but at the same time, like, I really love going home and just, like, yeah, disappear into the forest for, like, a day or a week. You know, let people know where you're headed, but just leave, like, get out, do something completely different. Main forest, yep. We went up to Sugarloaf, which is a ski resort up in Maine, and you know, if you go there during the winter, obviously you've got a lot of really cool skiing that you can do. But if you go there during the rest of the seasons, there's also really good like hiking trails and stuff like that. Not just like the ski slopes that you can hike. It's also like you could just go off and find some other trails in the woods. And they're pretty well marked and things like that. So I have not been to Yellowstone. It's kind of one of the places we want to go. Of course, we got to get out there before the superquake destroys everything, right? All right. So here's an interesting thing. We're going to use linear algebra here to, yeah, I've heard that. A lot of people really love it. I'd like to go out and see the buffalo and stuff like that. Wait. Am I thinking of the wrong one? Damn it. I live in this country. You'd think that I would know. Okay, you do get... Okay. What's the one in California? Yosemite. Okay, there we go. I never remember. It's just... Yeah. I've been to Colorado, and that was really cool, like, seeing the Rockies, you know, a few miles away. I mean, it was like 100 miles or something ridiculous like that. Nah, it's not that far, but, you know, it was really far, and we could still see the Rockies out there. They're just that big. It was really cool. Yep, have been to Oregon and Washington. Yep, we did kind of like that little trip down there from Seattle to Columbia River Gorge to Portland, or maybe reverse. Yeah, Portland, Columbia River Gorge, Seattle. Nice. Yeah, we really liked it. Didn't get much of a chance to, like, you know, stay there for super long time or anything. But, you know, we had like a week to do the whole thing, which is not nearly enough time, but it was still very nice. Just as a heads up, the microphone may just die, and if that's the case, my headphones have gone out too. And if that's the case, stream's over. I think we're good, because I think that this actually has been charging while I've been here. So I think it's actually higher than when it started instead of keep dropping. But it has been known to do that before, where like I got to, I don't know, 10% or something like that.
Check. That's really loud. Okay, give me 1 second. Let me fix that. Check. Maybe a little higher. Is that good? Okay. Yeah, I disabled my webcam microphone a long time ago because it was causing problems. And it's good in an emergency. Yeah, the problem was that the cord was resting against my shoulder, which sort of bent it, which then means that like the thing didn't connect properly, and it's a whole thing. And I didn't charge them last night like I'd meant to. Like I plugged in, yeah. I knew that it was at like 20, and I didn't know how long it was going to last, but it didn't even give me a warning. It, just whatever. All right, cool, whatever. That's default still. Okay, cool. Okay, so anyway, we'll keep going. I didn't know if it was just going to take too long to make that work, but yeah. We didn't get out too much, unfortunately, in Washington and Oregon, but we did get out a couple of times just to like walk around the city and then walk around like, a park or something like that, little miniature woods area. Okay. Didn't do Mount Rainier, no. We drove by it and it was very impressive, but I've heard. All right, so we're going to do a little linear algebra on this. So a plus b equals 0. It's an incoming raid. Amy I? No. May? Let me know how to pronounce your name. Welcome in to the rest of your family and raiders. I am Obi-Wan Pez. This is N Simplex Pachinko. We are doing some sorry. We're doing some math, so woo. Oh, that was fighting words, bud. I mean, I don't have a horse in that race, but nonetheless. Doing calculus homework? Yep. That's actually how I also started doing some research into how to stream. I was watching somebody else do their homework and was like, yeah, okay, just need to get some sort of desktop stuff. And then we ended up needing it because I'm also a professional teacher. AP Calculus AB, very nice. Sentient M, good evening. Yep, Calc 1. All right, we're going to be doing a little bit of linear algebra here in order to solve a simple system of equations. So, simple. So here we've got a negative square root, cube root of 5 times b plus c is equal to 0. We're going to kick this over just a little bit. We'll just do this one. Come on. Really? Come on. Fine. We'll do it this way. There we go. Well, thank you. I do like the business model. Yeah, my intention was just always to get, more teaching out there. I do hang out on the Discord, which is discord.gg/homework. And that's the entire invitation. discord.gg/homework. So hang out there occasionally, not a lot right now, because I'm just getting ready for my personal classes at work. So right. Normally my headset's on, but I accidentally ran its charge out to 0, so hooray. So at the moment we're doing some, this is a long-ranging problem. So we started out with a Calc 2 improper integral. It moved on to partial fractions, which moved on to factoring, which then moved on to trying to solve a linear system of equations, but now we've got cube roots as part of our good stuff there. I am not teaching series and sequences, or as we know it in the States, Calc 2. So that's not me this semester. And I would not dox myself, no offense, but I would not dox myself and say, oh yeah, sure, join my class. If you happened to join my school, then that would be an interesting coincidence. No offense. Is that because it's a high school? Or is it, no, it's college, right? It depends on where they draw the line. It also depends on how long your semesters are. If it's 15 weeks, then yeah, I'm not sure. But I think you also said that community college. Okay, yeah, right. You've also got something else going on. Oh, 6 weeks. That's it. Yep. That's why. All right. AI may. Well, anyway. Thank you for the raid. Have a good night. If anyone wants to lurk around or just needs to head out for the night, feel free. Normal quarter is 12 weeks. Okay, yeah. We are contemplating switching a bunch of our courses to 7-week. So that's going to be 7-1-7 for like having a break in the middle. And our regular 15-week courses are going to meet for the standard time, and all of our 7-week courses are going to meet for double the time. Makes sense. The problem that the registrar seems to have at the moment is that they can't figure out how to weight a 7-week class in anybody's schedule for twice as much. That's the easy part. As far as I'm concerned. Anything material of integral calculus is more workload than series and sequences. So it kind of depends on what you like. Everybody feels a little bit differently. It all depends on how well you did in that particular section, I think. At least that's, my opinion. I don't know how anybody else feels about it, but also, let's see. So for here, we're just going to do this. Let's multiply this whole thing by the cube root of 5. Reason being, we can clear this one out from A and just make it a simple. So this is just going to be 5 now. So 5A. And then minus this cube root combines with that cube root to make this cube root of 25 times C. Excuse me. And that's equal to 3 cube root of 5. Okay. Multivariates Calc 4, yep. and assume that's vector. Yep. Learned some vector and polar coordinates. Yes. So that's kind of an introductory piece that we usually work in to say, hey, just to let you know, there's alternate coordinate systems that you can use. Because in pre-calc, the whole point is like analysis and being able to do all sorts of crazy stuff. And then when you get into Calc 1, they assume that knowledge when you start doing some of the other stuff that's in like parameterization, U substitution. It kind of goes with Calc 2 for at least our class. Yeah. So when you start doing parameterization, you start trading out variables. That's where it gets a little bit different. Yep. Conic sections get way easier when you parameterize them. And that's usually why you bring them out. It's usually why you tell people about this like earlier on. Our curriculum does not have conic sections in it. My former boss, 2 deans ago, was like, we really need to get this into the curriculum. And I tried figuring out where to put it. We ended up doing it as like part of the honors section, and it was just dry and nobody liked it. And I only did it for like 2 semesters. And then I was like, you know what? Our pre-calculus honors section, we're just going to do math history instead. And so I taught math history. And people in the honors section seemed to really like it because it was just like a bunch of stories. It was just, let's talk about math. Let's talk about all the cool stuff that you all don't know about. Let's talk about it in chronological order. So instead of just skipping around all the time and saying, well, this was invented in like, ancient times, but then in the 1400s it was refined, and in the 1600s it was refined more, and in the 1800s it was refined more. And, here's the beginning, here's the end. That's basically all you get for, the history of math is like, this is where people were thinking, hey, I need a tool. And this is the tool we now have. It'd be like taking a hammer and being like, this is a hammer. This is the only hammer that ever existed. And like, clearly that's wrong. Or if you not, this is the only hammer that ever existed, but like, this is the hammer we use. This is the only one you ever need to think about. Like, that's not true. It's the only one that most people ever need to think about. A standard claw hammer. It's pretty good. But, if you want to, like, close a can of paint, you don't want to use a claw hammer. It dents up the whole top. It looks terrible. And if there's, like, paint on the inside, if you start denting the top, then it's not going to close properly, and then the paint's going to dry, and or if you drop the top, if you drop the paint can, it's going to pop off, and then there's going to be paint everywhere. Trust me, I worked in a hardware store. Ask me how I know. Engineering majors kind of split the difference between math and computer science, but it kind of depends on where you're going. So most engineers of any stripe will use computing software to do their job. They don't necessarily program stuff, but they're going to be using CAD as some sort of, design tool, or they're going to be doing, a whole bunch of stuff. Why not? Differential equations is so much fun. I know, you might not agree. It's fine. All right. So let's knock this out. So let's combine 1 and 3. So oh no. Well, we'll get you there. For any that you might need in the future. All right, so this is going to be I don't need to be paralyzed by the indecision. This is super easy at this point, but hey, get perfect score in Calc 2 except for differential equations. Oh. Let's do -5 of the bottom one. So equation 1 minus 5 times equation 3. It's going to be equal to, and here this is where we say, oh, no, backwards. 5 times equation 1 minus equation 3. All right, this is 1, this is 2, this is 3. Yeah. Always gets challenging. All right, so this is going to be 5a minus 5a, so that's going to be 0a. This is going to be 5 times equation 1 is going to get us a 5b. Okay, and then minus equation 3 is going to get us a positive cube root 25 times c is equal to a negative, equation 3 is going to get us a negative 3 cube root of 5. Okay, so then this is equation 4. And then we want equation 2 to combine with it, which is a negative cube root of 5b plus c is equal to 0. All right, least amount of work is going to be multiply least amount of work. Multiply the bottom equation by, so let's keep this somewhat in a similar space to what I had before. So we're going to do equation 4. We need 2 more cube roots here. So this is going to be 4 plus, there we go, cube root of 25 times equation 2. Okay, and then that's going to get us, well, that's going to get us not a mathematician, still know how to do an integral by instinct, right? Can't have screwed up your GPA that much. Oh, you can't screw it up because you need to get into UWCL. Yeah. So I don't think it's going to be, you know, I don't think you're going to do horribly. You just gotta watch your stuff from Calc 2. So that's going to be your big shortcoming. I would say that you want to go on to Khan Academy or wherever or here and work on that stuff like hard. So always work on the things that you have shortcomings on and you know it's a shortcoming. Organic chemistry. Woo! LL7, good evening and welcome. My name is Obi-Wan Pez. This is N-Simplex Pachinko, my home for all things mathematical. We do a Tuesday night math stream and a Friday night game stream. Zivizski. Zvizizi. Sorry. Thank you and welcome for the follow. Oh, yes. Thank you for the follow and welcome on in. If anyone does have any questions about mathematics, any particular stuff, we're kind of just faffing around at the moment. So feel free to drop in any questions you have in the chat, and I will get to them somewhat shortly. We're still doing a. I had a thing over there somewhere. Was a improper integral question, which is kind of morphed into this not so nice linear algebra problem. It's a simple 3x3 system of equations, and you know, preferably somewhat relevant. But my specialties are mathematics and education, and 2-year colleges. So if you have any questions relating to those sorts of things, that's especially welcome. If you have any other types of questions, yeah, I'll play it by ear. We'll figure out something. If it's like, awful, then sorry. All right, so we're going to take equation 4 just as is. Do I like riddles? Yes. I do actually do some puzzles here, and so like occasionally throw out some random stuff. So we'll see how it goes. They said, "What is this, a discrete math class?" So let's see. Equation 4 is going to get us 5. And then equation 5, right, I did this on purpose. The whole point was to subtract out the b, so that's gone. It's going to be 0b. Okay. Let's see. If one clock is to tick and the other is to talk, numbers in between say, well, all right, am I supposed to be thinking mathematically about this, or is this just like linguistic trick? Okay, so up here we've got a cube root of 25 times c. Down here we now have another cube root of 25 times c. So that's going to be 2 cube roots of 25 times c is equal to equation 4 is negative 3 cube roots of 5. So then we divide by this stuff, and so c is going to be equal to, haha, we have an actual number now. Negative 3 over 2 times the cube root of 5 over the cube root of 25. So that's going to be 1 each, or we can do this and rationalize the denominator, which, like, fine. We don't absolutely have to rationalize denominators, but you know. Alright, so that's going to be the cube root of 25 up top. And that's going to be a 2 times 5 down bottom, which is just going to be 10. So negative 3 cube roots of 25 all over 10. Yep. All right, so that's gross, but it works. So then that leads us to B up above, and also to A up above. So 5a is going to be equal to 3 cube roots of 5 plus cube root of 25 times c negative 3 cube roots of 25 over 10. All right, 5a is going to be equal to, this is 3 cube roots of 5 plus, that's going to be a minus. This is going to be 3 cube roots of 5, right, cube root of 5 cubed, it's just going to be 5. Divided by 10, we can get rid of the 5s in each of them. So here, this is going to get rid of it. No. Different color. All right, this is going to get rid of that if both of these go away and this gets rid of that. Gross, I know. That's going to be a minus 3 over 2 times the cube root of 5. And now these are somewhat nicely combinable. That's all right, LL7. But hey, thanks for stopping in. You're off to a flight. Ooh, nice. Well, I hope you have a good flight. Stay safe, and hope to see you again. Thank you for the follow. Have a good night. All right, 5a is equal to, here we have 3 minus 3 halves is going to be 3 halves. Cube root of 5. I mean, this is a problem that, like, I just made up off the spot, so that's not that big of a deal. But thank you. All right, so therefore a is going to be equal to, this is going to be our 3/10 now, times the cube root of 5. All right, so here's our a, here's our c, and then b. A plus b is equal to 0, so they have to be opposite values. That's the easy one. Always, always, always save that one for last. Right, whenever you, or not last necessarily, but whenever you've got the other term, just jump at it that way. All right, so then b is going to be equal to negative 3/10 cube root of 5. Woo. All right, so now the gross part. We got this stuff up here, where our a, b, and c all need to be plugged in. Woo! All right, so the initial coefficient is just going to be 1/3. All right, so this is coming in to say goodnight, so give me a second here. I'm going to run a quick 1-minute ad here, if I can, and we'll be right back. Oh, string manager. All right. Well, we'll wait for whenever she's coming. So this is going to be 1/3 times the integral of a, well, it's going to be 3/10 times the cube root of 5 divided by x minus the cube root of 5 dx. Okay, and then plus 1/3 integral of b, negative 3/10 cube root of 5 plus c, which was that, minus 3/10 cube root of 25 all over the quadratic that we had. So it's going to be x cubed plus cube root of 5x plus cube root of 25. All right, be back in just a minute. All right, so allegedly I'm back. It wouldn't show up on my phone at all. That's weird, but whatever, it's cool. All right, so this is our disgusting integral here that we're trying to figure out. There is also our natural log stuff that sticks out front there. So that's going to be our limit as b approaches infinity of the natural log absolute value of u, where x is going to go from 3 to b, plus that 1/3 out there and the rest of the stuff. Okay, so this 3/10 is just going to come out everywhere. That's perfectly fine. Oh, that one requires an x. So that's linear. All right, the 1/3 here can get rid of that. The 10th can come out. We end up with still no natural log absolute value of u was equal to x minus the cube root of 5. Nope, that wasn't it. Nope. X cubed minus 5. X goes from 3 to b. And to the limit as b goes to infinity of all that stuff. Okay. Plus, this is now going to be 1/10. 3b. Integral of dx over x minus cube root of 5. Worked perfectly well. Right, this is easy. That's also a natural log. So, simple enough. This one's a little more complicated. So I'm going to factor out a negative 3/10 and a root. Yeah. So this is going to be a negative 1/10 and a cube root of 5. So cube root of 5 over 10 is what we factor, or negative cube root of 5 over 10 is what we factored out. All right, then taking the integral from 3 to b of the entire first term is now just x minus 3/10 and one of those we factored out, so that's now going to be a cube root of 5. Okay, interesting. Over x squared plus cube root times x plus cube root 25 dx. So close. Okay, so if we let this be the new u, which I guess we could just call v, then dv is going to be equal to 2x plus the cube root of 5 dx. So we need a plus cube root of 5 dx, and we don't have it, so we need to add, right, we need to multiply our numerator by 2, which is going to multiply our denominator by 2 out here, right, balancing. And then we need to add to it in order to get this amount here. So we need a plus 1 on the inside. We're at a minus 2, so we need a plus 3 cube roots of 5 with a minus 3 cube roots of 5. Right, that'll keep everything balanced. That's really gross. All right. Sorry to anybody who just stopped in casually and was like, nope. All right, b goes to infinity of natural log. Now here's the thing. Y'all are going to be mad. Because we did a problem where the answer we could have actually found way up there. As soon as we did this natural log here, could have instantaneously said, we don't need any more. But that's not really the point, right? The point is to be able to say, no matter what the answer is, we want to be able to go through this process the same way, so that every time we go through this, we're always going to get the same thing. Sorry, not the same answer, but we're always going to get the same rigorous process that we go through. My pre-calc students are going to be very angry about that this semester. So we're going through very painstakingly and very carefully, and they have to understand how analysis works. All right, so this is going to be 1/10 natural log absolute value x minus the cube root of 5. And then in this group, this is going to be a minus cube root of 5 divided by 20 times the integral 3 to b of, now this is again 2x plus 1 cube root of 5 minus 3 cube roots of 5 for balance. All divided by. Yep. Hooray! So here we've got our x squared plus cube root of 5x plus cube root of 25. All right, you're not gonna like this. So I'm just gonna leave this limit here behind my head because it doesn't matter, right? None of this stuff's changing. It's all gonna be the same. So for the moment, it doesn't matter whether I leave it visible or not. You're gonna be able to see it, or you're gonna be able to see it just up here. All right, plus 1/10 natural log absolute value x minus cube root of 5. All right, minus cube root of 5 over 20. Okay, then this is going to be times the integral of, this is our dv over v, where we have all this stuff here. So that's going to be taken there. all of this stuff is going to be taken over here. Okay, so this is also a minus cube root of 5 over 20. And then the integral here is that we have a negative 3 cube root of 5 over that quadratic. X squared plus 3 cube root of 5 times x plus the cube root of 25 dx. All right, you're not going to like this. This one needs to be done by completing the square. All right, so you all are never going to have to do a problem that's this complicated and this ugly and this long, unless you're in like some seriously high level stuff. Like in your differential equations class, you might have to do something that's this ridiculously comprehensive. In Calc 2, I highly doubt it. Unless your teacher is giving you a like evil challenge problem. All right, limit b goes to infinity of natural log absolute value x cubed minus 5. X is going from 3 to b plus 1/10 natural log. That's also going from 3 to b. It's kind of important that you put the limits of integration on stuff. Yay. Absolute value x minus cube root of 5. 3 to b minus cube root of 5 over 20. This integral here is going to be, again, natural log. Absolute value, v is equal to this stuff. So x squared plus cube root of 5, x plus cube root of 25. All right, and we're going 3 to b again. All right, so then this last one. This becomes a little bit of a problem. We can't do that as is, so we need to complete the square. All right, c needs to be equal to 1/2 b parentheses squared. So if you remember, this thing should be like ax squared plus bx plus c. A is 1 in this case, and so that makes this middle term a little bit easier. We're going to be dealing with this in terms of thinking of this as x plus something squared. So here, this is going to be x squared plus 2a blank x. Yeah. Well, a's 1. What am I doing? 2 blank x plus blank squared. So what we really need here is a blank squared in the last term and figure out what that is based on this thing. So based on the fact that our x term, our linear term, is more complicated, is harder to figure out, is not going to work very nicely for us if we try to like change it, because then that introduces more linear terms and we don't want that. We can change constants, that's okay, because like we saw up above, right, with our cube root of 5, right, the constant term, you can just add and subtract a constant and then it makes it much easier. So in this particular case, 1/2 b is going to be 1/2 cube root of 5, and then we're squaring it. So this blank is going to be equal to 1/2 cube root of 5 parentheses squared. So it's going to be 1/4 the cube root of 25. Okay. So that is going to be in here. We've got now an integral. I'll leave it where it is right now. So -3 cube root of 5 divided by, here at the bottom we're going to have x plus, and again this is what we've got, 1/4 cube root of 25 parentheses squared dx. All right, now this becomes a trig integral. So we've got to solve the trig integral. All right, so at this point, all of this stuff is just going to be dot, dot, dot. Okay, minus cube root of 5 over 20 times the integral going from 3 to b, -3 cube root of 5 over. So trig integrals, we say here, this looks an awful lot like something all squared. Oh, nuts. Maybe it's not a trig integral. Hang on. Is it inverse trig? Oh, no, that's fine. Okay, we're good. Yeah, I got ahead of myself there. We're good. So, this is just another u substitution. Yeah, I was thinking trig, but trig is when the x is squared, and then you have your like a squared or whatever. So that would end up being like x squared plus a squared would end up being a inverse tangent. So in this case, because it's all parentheses squared, that's just a u sub. So the u here is all this, which I guess we can call. We'll just call it a u substitution and not use u. It's fine. So when we do this, we end up with, u squared at the bottom and a du at the top, because here we don't have any constants. When you take the derivative of the inside of this stuff, it's just 1 dx. So that's it. So actually we can take this out. Because we did a u substitution, we can just show what happened to it. So in a u substitution, the integral of 1 over u squared du is going to be equal to -1 over u. Let's see. So this is going to be a, right? Yeah. -1 times that. So this is now going to be a positive 3 cube root of 5 divided by x plus 1/4 cube root of 25. These will combine. Let's keep the constants just out front, make it easier. And then that's going to be from 3 to b. Okay, so this means that here we're going to have all the same stuff. Limit b goes to infinity of, right, we don't need that set of parentheses. Just go from there. natural log, absolute value, x cubed minus 5, going from 3 to b. Let's take the quadratic and move that a little bit up front. So minus cube root of 5 over 20 times the natural log, absolute value, x squared plus cube root of 5 times x plus cube root of 25 from 3 to b. Okay, plus 1/10 natural log, absolute value x minus cube root of 5, going from 3 to b, and a negative here, 3 cube roots of 25 over 20 times 1 over x plus 1/4 cube roots of 25 plus c. Alright, so that's the integral portion. Then the next part is, what do you do when you take the limit as b goes to infinity? Well, immediately you can see that right here, b going to infinity is going to cause this thing, the argument of the natural log, to go to infinity, which causes the natural log to go to infinity. So, there you go. I will say that this also creates a small problem in terms of the fact that this is going to be a positive infinity here, minus infinity here, plus infinity here, and minus infinity here. Or, well, actually, no, this is going to go to 0 because the x is in the denominator. So infinity minus infinity plus infinity minus 0 plus c. But again, since we're doing definite integral, we don't need it. All right, and since we have this infinity minus infinity, technically this is an indeterminate form. So we'd want to like double check to see how this is going to go, but realistically, right, this is going to be, we could combine them as a natural log. That could work, right? Can do this as natural log of the absolute value of x cubed minus 5 divided by your x squared plus cube root of 5x plus cube root of 25. And the denominator here is raised to the negative cube root of 5/20th power. I mean, we could have even just left it with that. Right, if we flip it to the top now, it's going to be natural log absolute value x cubed minus 5 multiplied by x squared plus cube root of 5x plus cube root of 25. Okay, so we take this and this becomes a positive exponent on the top. All right, well, that with our natural log here is going to produce, as x gets really, really big, it's just going to go off to infinity. So this particular integral goes off to infinity. It's not really a surprise for anybody who has studied basic. Yeah. Anybody who's done a lot of work with anybody who's done work with like rational functions beyond pre-calc, you can look at this and say, well, you know, the denominator has a higher power, so it should go to 0. But the problem here is that the difference in their degrees is only 1. So this is going to have a behavior which is very similar to the integral of 1 over x. And Blainland, this is where your infinite, or your series and sequences stuff comes in. So if we want to know what the integral of 3 to infinity is going to look like for x squared plus 1 over x cubed minus 5 dx, right? The entire point of the Calc 2 stuff that we were doing was to look at, sorry, that's your Calc 3. The entire point is to look at this and say, all right, well, we know what sorts of things we have here. Let's figure out what the behavior is. So what we'd have to do in this particular case is find a find a particular method to look at these and say what's happening as we go further and further out. So if I went with this and Calc 2, all the different comparison tests. We can do a limit comparison test. Hey, Paul's online. All right. Oh, that one's good. I like that. All right, so this is easy enough to say that this is analogous to an integral going from 3 to infinity of 1 over x. So what we do is we say, okay, in terms of our series, if we did n goes from 1 to infinity of n squared plus 1 over n cubed minus 5, this would be, again, analogous to n goes from 1 to infinity of n squared over n cubed, which would be equal to this thing, right, 1 over n. All right, the sum as we go to 1 over n. There's also a few other things that we can try. Let's see, what does 1 over n do compared to the original? So if n is 1, we'll just do a table here. It's fine. 1, 2, 3, 4, 5. Okay, we got 1 over n, which is just going to be 1 half, third, fourth, fifth. And then n squared plus 1 over n cubed minus 5 is going to be 2 over negative 4. That's going to be negative a half. We're going from 3, so it doesn't really matter anyway. But 2 is going to be 8 minus 5 is 3 on the bottom, and 5 on top. Alright, so now we get serious. So 3 squared is 9 plus 1 is 10. Divided by 3 cubed is 27 minus 5 is going to be 22. So it's going to be a 5/11. So yeah, actually this should be like from 3 to infinity because we're only including those numbers, not 1. Alright, 4 is going to make 17. That's nice. Prime number, don't have to worry about it. And on the bottom we have 64 minus 5 is going to be 59. Ugh. It's a little gross, but it's bigger. Is that going to be helpful? Yes. Yes, yes, yes. Okay. Alright, 5 is going to be 25 plus 1 is 26. Over 5 is going to be 125 minus 5 is 120. So 13 over 60. 12 over 60 is 1/5. So again, this one's bigger. So as we go through, and this is going to be important, the sum as n squared plus 1 over n cubed minus 5 goes from n equals 3 to infinity. We end up with the individual terms being greater. So here, a sub n is going to be greater than or equal to, technically, 1 over n. For all n belonging to the integers greater than or equal to 3. This is bad notation, by the way, but whatever, it's fine. Anybody reading it should be able to understand it pretty well. Alright, since a sub n is greater than or equal to 1 over n, and n goes from 3 to infinity of 1 over n diverges, then sum as n goes from 3 to infinity of n squared plus 1 over n cubed plus 5 also diverges. This is a really powerful method. If you know a few comparison pieces to try out, then you can end up figuring out that an integral is possible or not possible almost immediately. And you don't have to go through all that other junk that we did up there. You don't have to do the partial fractions. You don't have to even figure it out unless this comparison works. If this comparison yielded something that got us a finite value, said that it converged, and definitely converged, not just like, maybe, then we'd have to go through and do all the work. So for instance, if I just change the bottom to be x to the 4th minus 5. So let's do a hypothetical here. If we made this the integral as, or of, x squared plus 1 over x to the 4th minus 5 dx from 3 to infinity. Then in this particular case, we'd be saying, all right, let's try out the table of values maybe. It's not particularly nice, but no, 3. 6. And that's going to be sufficient. Alright, so this is going to be 1 over n squared, and then this is going to be n squared plus 1 over n to the 4th minus 5. Alright, the difference in their degrees is 2, and the denominator has 2 higher degrees than the numerator. So the ratio of these two things, our rational function, should have an asymptote that has the same behavior as 1 over n squared. We know that that asymptote is y equals 0, so it should converge to a particular value. The individual values are going to converge to 0. But now we got to go and say, all right, well, the individual values go to 0, but what about the sum of all of them? So that's what this comparison test is really doing. Okay, so here, our 3 is going to get us 1/9. 4 is going to be 1/16. 5 is 1/25. And 6 is 1/36. All right, 3 plugged into here is going to get us, again, 10. But divided by, this is 81 minus 5 is going to be 76. Okay, 4 is going to get us 17. 5 is going to get us 26, and 6 is going to get us 37. Let's just do all the numerators, it's easier that way. 4 is going to get us 16 times 16 is 256, minus 5 is 251. 5 to the 4th is going to be 625 minus 5, so 620. And 6 to the 4th power is 216 times 6. So 9 and 12. 1296. Yep. All right. Do I care about the particular simplified versions? No, I don't. Because right now, all I really need to compare is just what are the individual numbers. And oh no, idiot, why did you buy this? I was like, yeah, it'd be great to have a 4-function calculator just kind of laying around for, the kids, just in case they want it. Yep, that's great. It's got a maze on the back. I was like, oh no, the battery's loose. That's not the battery. All right, so 10 over 76 is 0.1315. Some other stuff. 17 over 251 is going to be a 0.067. 26 over 620 is 0.041, and 37 over 1296 is going to be 0.2 2, 8, 5. All right, so 1/36 is going to be 0.277. 1/25 is exactly 0.04. 1/16 is 0. I used to know this. 625. And 1/9 is 0.1 repeated. Object Sphinx. Good evening. How's it going? So in this particular case, what we have is that our is that what I want? I don't think I want that. No, I don't. Damn. In this case, our sum for 1/n² is, the individual values. So the individual values of 1/n² are all less than the individual values for n² plus 1 over n to the 4th minus 5, which is not helping. So it's not doing anything for us at the moment. On the other hand, we should be able to just transform the comparison and say, what about 1/n minus 5 squared, n minus 3 squared? So maybe this will do it. Let's see. All right, so 1/n minus 3. 3 we can't do, so maybe that was a problem. N minus 2. Sure, we'll let it be that. Just because that's the next integer over and it's just easy to work with. Okay, so let's do n minus 2. All right, so with the value of 3, this is going to be 1. And I want my comparison to be bigger. Yes, we're good. Okay, so then I say at 4, we're going to get 2, and that's squared, so that's 1/4. Five minus 2 is 3, squared is 9, so 1/9. And 6 minus 2 is 4, squared is 16. So this is going to be 1, 0.25, 0.11, and 0.06. Nope. 0.062. Jeez. No wonder. 0.0625. All right, now that we look at it, this stuff here, 1/n minus 2 parentheses squared, is always going to be greater than n² plus 1 over n to the 4th minus 5. Always. And if you want, you can actually work it out by like trying to solve this equation and see what kinds of things you get. Yeah. All right, 4, again, n greater than or equal to 3. So for all these values, again, these are bigger than these. We can see that very clearly. It's a 0.0285. Again. Oy. And that's a 0.0227 or 277. Okay, so with this as it is, we're saying that we have this function 1/n minus 2 squared, which is always going to be greater Okay, so this is going to be, I don't need to put n equals, just say n axis. This is going to be 2. Okay, and forgive me, this is going to look a little weird, but whatever. At 3, 4, and 5, and 6, it has values of 1. It's fine. Values of 1, 0.25, 0.11, 0.06, so like almost half. Okay. And then this one here, again, we have values of point. No. 0.11, which is going to be pretty close to here. 0.13, so a little bit higher than that one, but whatever, it's fine. 0.067, which is going to be here. 0.041, which is going to be here. 0.0285, which is going to be here. And they're going to both just keep getting lower and lower as we keep going out that way. Again, you can prove that all of them will be, all of the ones in this will be higher than all the ones in this, but, you know, for n being greater than or equal to 3, everything is positive, all the terms are positive, so we're going to get an n to the 4th minus 5 is greater than n squared plus 1 times n minus 2 parentheses squared. Okay, so here we're going to have n to the 4th minus 5 greater than n to the 4th. This is n squared minus 2n plus 4. That's a 4. Right, 2 AB. All right, then we multiply that by n squared plus 1. So here we get n to the 4th. Here we're going to get an n to the 3rd. And nowhere else are we going to get n to the 3rd. So minus 4n to the 3rd. We get an n squared out of multiplying this one by the constant. So that's going to be a positive 4. And multiplying this one by that constant, which is a 1. So positive 4 plus 1 is going to be a positive 5 n squared. Okay, linear term, we're going to get n. And then minus 2. Alright, so those are all the coefficients that we're going to get for that thing. This can come over, or this stuff can go over that way. I don't really care. 0 is greater than. So we're going to get a negative number. This is 4n to the 3rd plus 5n squared plus n minus, no, plus 3 for all n values greater than or equal to 3. So if we plug in 3 into this thing, we're going to end up with n cubed is a 27 times 4. So that's a 98. Nope, it's bigger than that, isn't it? Yeah, 118. 27. Oops. 27 times 4. 108. Jeez, man. I'm okay, I promise. Alright, so we're going to get a negative 108 here. And then on this term, we're going to get 9 times 5 is 45. So that's like, you know, not even half. So there's no way to come back from that. On the next one, it's going to be, n equals 4 is going to get you 4 cubed is 64, and 4 squared is 16. That's a huge difference between those numbers, and it's just going to keep getting bigger. So we know for all n greater than or equal to 3, this is going to be true. This is always going to yield a negative number, and therefore this is always going to be greater than this, and therefore our denominator is going to go to 0, well, that was the case with both of these. Sorry, this is going to be greater than that. Right, as long as your n is greater than or equal to 3, that means that our the black comparison test will always be higher than the red original that we want to test. So this is going to say that since 1 over n minus 2 parentheses squared is greater than n squared plus 1 over n to the 4th minus 5 for all n greater than or equal to 3, and the sum as n goes from 3 to infinity of 1 over n minus 2 parentheses squared converges, right? This is a higher value that we know has a finite sum. So therefore, if all of the other ones have lower values, it's got to converge too, because the sum of those numbers all has to be less than a finite number. So it's going to be another finite number. Right, then sum as n goes from 3 to infinity of n squared plus 1 over n to the 4th minus 5 will also converge. And therefore, the integral going from 3 to infinity of n squared plus 1 over n to the 4th minus 5 dx, x and dx, x squared plus 1 over x to the 4th minus 5 dx converges. So here you run a test first and say, yes, look, this does converge. Now, what does it converge to? All right, so this is where you'd break out all those rules that we talked about up there in order to find out when this particular problem or what value this particular integral has. All right, is there anyone here who has a question? I'll give you about a minute or two just to speak up and say yes, and then another minute or two after. Well, I'll let you type it out. Not just a minute or two. That's fine. If you say yes. All right, there's only two of us in here, so. All right, I think we're going to call it for the night. Thank you, everybody, for coming. Sizzy, yeah, or Zissy. Apologies. Thank you for the follow. LL7 Sentient, Thank you for the follow also. A Seeker 101, thank you. Thanks for the follow also. So, my name is Obi-Wan Pez. This is N Simplex Pachinko. We do math on Wednesday. Nope, we do math on Tuesday nights now. Tuesday nights. I'll get it eventually. And we do games on Fridays. So, lately we've been doing Oberdin and have been having a good time with it. We're getting toward the end. If you've never played it, try to see if it's on Game Pass, and if not, yeah, I mean, I can't tell everybody to get it, but I like it. It's quite good. Of a murder mystery sort of thing. You are playing an insurance adjuster who is standing on the ship of an East India Company vessel that has arrived in port after 4 years of being disappeared. So I like it an awful lot. So we are going to read out to somebody probably playing something, as I don't see anyone who is also doing math. Oh no. Oh no. Okay. Let's head over to Boss Lady. She is one of our usual raid targets because she has some fun stories, and she's playing Farthest Frontier tonight. I'm not sure exactly what that is. Never seen it before, so let's go. So, thank you again for following, for coming on in, for exploring math with us. We'll be back on Tuesday for math, and this Friday for the conclusion of Return of Oberdin. So thank you very much. I'll see you later. This is Obi-Wan Pez for N Simplex Pachinko. Have a good night.